Hello again, everybody. Welcome to session number 5 of GG497 Geological Visualization, where today we're going to look at dipping strata and dipping geological features and how they express themselves on maps. As we recall from the previous couple of weeks, we first looked at horizontal beds, those which have flat or horizontal contacts between them, and showed that geological strata that have these sorts of contact, these horizontal bedding planes, when you put them on geological maps, you'll see that the outcrop patterns are parallel to the ground contours. However, often in geology, rocks aren't horizontal and other features aren't horizontal. Quite often they'll have some sort of dip to them. So our question is, how do non-horizontal phenomena appear on geological maps and sections? So for example, if you have a series of sedimentary rocks that have been tilted during some sort of tectonic deformation, their dip will no longer be horizontal, it'll vary somewhere between the horizontal and vertical. And what we need to understand is how dipping rocks appear on a geological map. If we start with the most simple example, then, if we think of a block diagram where we have an interbed of, say, a sandstone within mudstones either side of it, if that ground surface is perfectly flat, perfectly planar, then the outcrop of that sandstone will appear as a strip bounded by parallel lines. Now you can imagine that if this was originally horizontal, this sandstone bed was originally horizontal, and then we've tilted it and then eroded down through the stratigraphy to form a modern day weathering surface. You can imagine that tilted bed, it's only ever going to crop out as a strip. If we were to introduce some topography to that ground surface then, and look at that in a block diagram, so here we have another tilted sedimentary bed within a package of other sedimentary rocks, and you can see that if we were to look down on that topographic surface, you'd see that the outcrop pattern, it would bend, it would interact, and it would deflect around the ground contours. And at this point we have seen the three potential outcrop patterns that you can really get in geology and in maps. We've got the horizontal ones, where your outcrop patterns are parallel to the ground contours. We've seen the vertical ones, where our vertical features, their outcrop patterns just cut across the ground contours without any deflection or interaction with them. They just carry on straight and linear. But now we're seeing dipping contacts where the beds have some angle of dip, somewhere between 0 and 90, and you can see that their outcrop patterns will deflect and run along and interact with the ground contours. They'll still cut across them in places, but in other places they'll bend around them. So whenever you see a geological map that has 1, 2, or 3 of these different outcrop patterns, you immediately know something about the orientation of the beds. You know if they're flat lying or if they're vertical or if they have some angle of dip to them. So for example, looking at a geological map, this is of an area near Brecon and Swansea, and the Liberty Stadium is somewhere to the south of us, about 20 miles to the south of this map. And you can see that we've got these ground contours, these faint brown lines, some of them are dotted, that show the ground surface. And you can see that these dashed lines, they're showing us our geological contacts. And if we follow them around, just follow one of them. For this, for example, you can see that it bends around, it's deflected by the topography, it cuts across contour lines, and it has a sort of wiggle across the landscape, which is different to what we've seen for horizontal features, or indeed steep near vertical features like this fault, for example, which just continues straight across the landscape without being deflected by any of the ground contours. Okay, there's something in map interpretation which we call the V rule of dipping contacts. And there's two parts of this V rule, and the first part says that if you've got a contact that dips upstream, if you look at this block diagram, you can see that the ground surface we're at high ground height here, low ground height there, so this direction is downstream, and then this direction is upstream. And you can see that if your sedimentary rocks are dipping in the upstream direction, the V of the outcrop pattern will be in the same direction as the V of the ground contours. Can you see that we have this bed of sedimentary rocks that's dipping upstream, and when we look at that map surface straight down in map view, you can see that the V of the outcrop is pointing in the same direction as the V of the ground contours. Now if we go back to our map of Brecon, you can see that we've got these two mountains, and you can see, if you follow the light brown outlines of the ground contours, can you see that they V in this direction? And you can see that the dashed lines of the geological contacts, which I'm following now, they too V in the same direction. And if you look closely, you can also see that there are dip arrows telling you the direction of dip, and yes, they're pointing upstream. So this is a good example of where the V rule holds true. So that's the first part of it. If your dipping sedimentary rocks are dipping in an upstream direction, then the V that the outcrop will make will point in the same direction as the V of the ground contours. The other part of the V rule then is if you have the opposite scenario where your beds of sedimentary rocks are dipping downstream, then the V of the outcrop pattern will point in the opposite direction to the V of the ground contours. So you can see that we have this bed of sedimentary rocks in our sedimentary package. It's dipping in the direction of downstream, and the outcrop pattern that they produce, that V-shaped outcrop pattern, will be Ving in the opposite direction to the V created by the ground contours. Okay, so that's sort of just quite general ways to figure out what the general direction of dip of the rocks in your map areas before you even look at anything like structural contours or get to grips with looking at the dip amounts. You can get a feel for the orientation of beds from geological map just by looking at the interaction and looking out for V rules in different areas. Okay, but then let's say that we want to quantify the actual dip on a map. It's not just enough to say we've got a vague direction. We want to be specific, and we want to give an actual number to the amount of dip. Well, hopefully you guys remember from last lecture that inclined surfaces like bedding planes, for example, have these three structural components which define the geometry of that bedding plane. The first component is the strike, and that's a horizontal line that you can draw along the surface of that plane. If you think about this plane, we could draw infinite number of lines all over it, but there'd only be one of them which would be perfectly horizontal, and we call that line the strike. The second component of our measurement is the dip, and that's the maximum angle between the horizontal and the dipping surface. Okay, and I guess there could be any number of angles between the horizontal and the dipping surface, but the dip, the true dip, is the maximum. It's the steepest angle down that surface relative to the horizontal. And then lastly, the dip direction. That's the direction within the horizontal plane that dip is oriented. Okay, it's always 90 degrees to strike. It's always perpendicular to strike. And so once you have either the strike or the dip direction worked out on your compass, you can do a simple subtraction to find the other. So to summarize that, the dip is just the angle of tilt, the maximum angle of tilt from the horizontal to the surface of the plane. Strike is the direction of the only horizontal line that you can draw along the surface of that inclined plane. And the dip direction is the horizontal orientation in the direction of dip. Okay, dip is measured as a number between 0 and 90. Both strike and dip direction are recorded as a 3-figure compass bearing. And as long as you write them down, and for the first few times, especially in your early field trips, if you were to write in your notebook what each one of these 3 is, and then you can develop your own notation that'll make sense to you. But right now I try and be explicit in your notes. Okay, on geological maps, there's 1 or 2 ways really that dip is codified or recorded on there. The most common way, and the way that you'll probably do most of your dissertation work in, is to use this bedding symbol. And it's an elegant way of recording the structural information, all 3 of those components for the dipping planes that we just talked about. Okay, so if we zoom in on that symbol, the number that you can see refers to the dip. So that's the angle from the horizontal down to that inclined plane, the dip angle of the plane. The long part of this line is oriented parallel to strike. So all maps will have a direction of north somewhere on them, either through orientation to the grid lines or north arrow or the orientation of the text. And that long part of the symbol has been oriented that way to be parallel to strike. So north has a bearing of 0, 0, 0, and then we simply count around clockwise the size of the angle between the north arrow and the strike, and once we have that orientation we draw that on our map. So in our case the orientation of strike is 160, and that's because this angle in here is 160. Then you'll see that the symbol has this other component, this little tick, and that little tick is on this side of the line because it's pointing in the direction of dip. You know, this little line, you can't put it on that side because that would say it's pointing in the opposite direction, but in our case our dip direction for our rocks is towards 070, so we point it off to east-northeast. Okay, so again, because dip direction is a compass bearing, it's always measured clockwise from north, so we count around from the north arrow to the direction of dip, mark on the symbol in the correct orientation, and by doing that the angle between the dip direction tick and the strike line will always be perpendicular. It will always be 90 degrees. Okay, on a map only the dip amount is recorded in number format. The strike and the dip direction, they're recorded by the orientation of the symbol. If you really wanted to measure the strike of rock, then you could measure one of these dip symbols using your compass or a protractor, but the key point is you don't put those numbers on. The numbers are stored within the symbol. You can imagine that if you put all three sets of numbers on a geological map, it would become extremely confusing and very busy straight away. That's why we only record the dip amount and use the symbol to show the direction of strike and dip direction. Okay, that's probably the most common way that I've seen dip recorded, but another way that some people record the dip is by using this arrow. And this sort of arrow, and it's always worth double checking in the key, this arrow works in a slightly different way, and basically it's oriented so that the arrow is pointing in the direction of dip, the dip direction. The little number still refers to the amount of dip, so that's the same between the two symbols. But in this case, the arrow is pointing in the direction of dip. If you then wanted to calculate strike, you could just take 90 degrees away from that dip direction in order to get the strike direction. But when you see this symbol, it's important to remember that it's pointing you in the direction of dip. Okay, sometimes you'll have a map that doesn't have any dips and strikes. You can tell that it's dipping because you can tell these rocks are dipping because the geological contacts, they kind of cut across the ground contours and they wiggle their way around, they deflect around them and then cut across them. So you can tell that it's not a horizontally bedded rock because they'd be parallel to the ground contours, and you can tell that it's not a vertically bedded rock or vertically oriented rock because it doesn't cut straight across the contours. So if you have this sort of situation, how could you estimate the dip of the bed? If you think to yourself maybe from the previous lecture from last week, you should arrive at the answer of maybe structural contours. Now, in order to draw structural contours for a bedding surface, we need to be able to join points along the geological boundary where we know the height of it. And what we did last week was to join points along the contact where they intersect ground contours of known height. So for example, here the geological contact crosses the 1850 feet ground contour, and I apologize for this, this is a relatively old map, so it's in imperial measurement. But if we were to follow that contour around the map, we'd see that it would also cross our geological contact there. So we've got these 2 points where we can draw a structural contour between them. We can do the same thing for the 1800 and the 1750. So now that we've got these structural contours, we can start figuring out what the direction of dip is, what the strike is, and what the dip amount is. Now, remembering from last week, you remember that if these structural contour lines are connecting points of equal height, then by definition they're horizontal. And if the strike is a horizontal line along the plane, then you can see that the strike direction is going to be parallel to the structural contours. So once we've drawn these structural contours, we can just use a compass or a protractor to figure out their orientation, and that'll give us strike. Then we have a 50-50 chance, I guess, of getting the dip direction. It could either be dipping in this way, or it could be dipping in this direction, perpendicular to strike. But again, if we look at our labels for our structural contours, we can see that we start off higher here at 1850 and drop down to 1750 here. So the slope is going from north to south. So this is the dip direction. This is the downhill direction, I guess, on our bedding plane. Then what we could do is use a little bit of trigonometry to measure over how much horizontal distance d our vertical change between two structural contours happens. So for example, our vertical distance would be 100 feet, which is about what, 33 meters, something like that. And then we could measure over what horizontal distance that occurs using the map scale. Taking the inverse tangent of that relationship would give us the angle of dip of our bed. Okay, so that kind of summarizes the ways in which we can figure out the dip of rocks from a map. We can use outcrop patterns and the V rule to figure out a general direction of dip, or indeed the presence of any dip. Then we can either use the map symbols, which have been written on the map to show us the dip and strike and dip direction of the beds, whether they be the standard bedding symbol or one of these arrows. Or if you're really pushed and you really need to know the dip of these beds, then you could attempt to draw structural contours for different regions of your map. Okay, well, let's have a look at an example, a bigger example, much more involved than the example that we did last week of how to draw a cross section for dipping rocks. Okay, so this is an example from the Penrith map sheet where we have 3 packages of rocks. These sort of lighter greys, sort of almost washed out browns, they're the millstone grits. Then we have these darker greys with these darker sort of mustardy yellows, they're the coal measures. And then these orange are the Penrith, or the Penrith sandstones, rather. And let's say that we wanted to draw a cross section between points A and B in order to show the subsurface geology. Okay, immediately what we can see is that these rocks, they're forming these strip-like outcrops. You can make out in some places the contour lines, like here's one there, wiggling away across the landscape. I think it comes back up here. And you can see that these rocks, they're not parallel to those ground contours, they're forming these strips that are slightly deflected by the ground contours, but forming strips nonetheless. You can also see that in some locations, the geologists who mapped this have recorded dips of some of those beds. So about 12 degrees here towards dipping towards the northeast, striking northwest, southeast. Here there's another bedding reading that says that those rocks are dipping at about 5 degrees, dipping towards the east. And all of that looks quite consistent. There isn't anything that would indicate that we've got some sort of folding or anything other than rocks which are uniformly dipping in largely the same direction. Okay, so for this example, because we've got dipping rocks, you don't necessarily need to draw or plot an entire hill profile. You can produce what we call instead a sketch cross section, which just really limits itself to the geology. So once we've got our eye in, we know kind of what's going on, let's start figuring some things out and start recording some data for our plotting our cross section. So our first step then, like with others, is to use a strip of paper to mark on the geological contacts. So everywhere along here, what I've done is marked on a geological contact, and some of those contacts are going to be stratigraphic. They're going to be the contact between different rock types, and some of them are structural. You can see that we have this northwest southeast trending fault, and what I've done just to tell it apart from the structural contact is to plot it with a different color. So I've got all of that in, and I've labeled them. And then what I'm going to do is, between my contact marks, I'm going to color in the or symbolize the rock that would appear on the cross section between those two contact marks. So here I've got my millstone grits, then I'm into my coal measures, and then I'm into my Penrith sandstones, and here I've got a nice little dyke chap that's just intruded the stratigraphy. Now what I'm going to do, I mean I could have done this earlier if I'd thought about it methodically, but what I'm going to do now is remove the strip of paper and check to see if there's any information that constrains, spelling error on the slide there, that constrains the dip of the contacts. Okay, and I can see that I've got this fairly consistent dip, or there's another dip angle there that's in the vicinity of my cross section. But in this example, and only in this example, I'm just going to ignore that and use 35 degrees just to prove a point. If anyone who is watching this has a better map which shows nice parallel bedded uniformly dipping rocks that has an angle that would look better on a cross section, I'd really appreciate the heads up. But right now I want you to just accept that I'm going to draw these at 35 degrees just to prove a point. Okay? Alright, so those are the sedimentary rocks. So I'm going to use that as the dip of the sedimentary rocks, but I can't use that as the dip for every single feature that we're going to run across. For example, other than the sedimentary rock contacts, on this cross section I've also got a fault, and I've also got a dyke to take care of, which aren't necessarily dipping at those same angles. Okay, so if we focus in on that fault and that dyke, we can see that we don't have any quantitative information recorded about the dip of the fault and the dyke. Like, we don't have a dip angle, we don't have some sort of number that would tell us the angle of dip. So we're going to have to try and work it out from the outcrop pattern itself. So if we look at both the fault and the dyke, we can see that neither of them are really deflected by the topography. You know, they're pretty much linear all the way across the map area that we can see, right? Like if we follow this fault down, it's almost a dead straight line. It just cuts across. We've even got some ground contours here. It just cuts straight across that ground contour as if they weren't even there. Same thing goes for the dyke. It just cuts straight across them like as if they weren't there at all. That sort of outcrop pattern, as we saw in the previous lectures, means that these features are probably close to, almost, whatever you want to call it, vertical, or at least really steeply dipping. Okay, at this point, unless we were to draw structural contours for these, which may or may not give us any more information, I'm going to assume that these are near as possible to vertical or sub-vertical, if you want to split hairs about it. So then what I would do is put my cross-section panel back on to my map, and I'd add in some structural information about the dip of those faults. Because they're vertical, you know, vertical is the same as having a 90-degree dip. Okay, so now I've got all of the rock types on my map, or on my cross-section strip. I've got all of the contacts, and I've got all of the structural information that I need, all of the dips for the beds, and the dip of the fault, and the inferred dip for the dyke. Okay, so now we can start plotting our section. And because our rocks are dipping, we can, or we usually assume, a flat topography. We don't need to show all of the hills and valleys in order to see the subsurface rocks. You remember the map that we did for Sidmouth? If we didn't have a vertically exaggerated topography, then we'd have the most boring cross-section on the planet. We'd just see a series of really closely stacked horizontal lines. Because our rocks, and this is why I've changed the dip to 35, because they've got an appreciable amount of dip, we don't need to do any of that. We can still see the geology without having to rely on an over-accentuated topography. So then that makes the first step really simple. You just need to take your geological contacts, drop them onto the top of your cross-section panel, and mark on where on the surface of that cross-section you'd hit those contacts. Then what we can do is, again, I always like to do this, maybe some people would disagree, but you can shade your cross-section surface in the appropriate color, just a very thin veneer. You don't want to go like too far down because you're going to draw these things at angles. So I draw it as a very thin veneer, probably even thinner than what the PowerPoint currently represents, but just to show the geology that you'd encounter at the surface at those points. Okay, at this point we can't just, go a bit gung-ho and just start plotting things in. We need to think about the order in which we're going to plot our geological features. We need to really investigate our map to see if we have any cross-cutting relationships which are going to affect the order in which we draw our cross-section. So if we look back at our map, we can see that we do have two really key cross-cutting relationships. One of them is that we have the sedimentary rocks that have been cross-cut by this dike. So there's one of these cross-cutting relationships there. And then the other cross-cutting relationship is that we can see we've got these sedimentary rocks, and look, we've got a contact, a stratigraphic contact between the Penrith sandstone and the coal measures. And if we follow that contact down a long strike, we can see that it's been cross-cut by this fault. So we've got these cross-cutting relationships, and we now need to decide which are the youngest features, plot those first on our cross-section, and then work our way backwards. Okay, so for us this is a fairly easy example. We can tell that the dike is younger than the sedimentary rocks because it cuts all the way through them. So the sedimentary rocks must have been there first in order for the dike to intrude them. That makes sense. And similarly, the sedimentary rocks must be older than the fault, because again, the sedimentary rocks must have already existed in order for them to have been faulted. So we can tell that the youngest features are the fault and the dike. We can't tell which is younger between the fault and the dike because we can't see a cross-cutting relationship, at least in this part of our map. Maybe if we went further to the north they seem to converge, but right now, based on our map, we can't tell if there's a cross-cutting relationship between them. So what we can do then is, once we've got these two youngest features, we can plot these on our cross-section. So at this point we can plot the subsurface extension of these youngest features, in our case the fault and the dike. And because of their outcrop patterns, and because we haven't drawn any structural contours or anything like that, I'm going to draw them as vertical features. They look pretty darn steep on map view. Look at the way they don't get deflected by the ground contours. Same for the dike. I'm going to draw them as vertical features. If I need to change it later, that's fine in light of new evidence, but right now I'm going to think of them as subvertical features. Okay, then what I can do is plot the subsurface extension of the older material. So we've just done the youngest features, we've done the dike and we've done the fault, and now we can start plotting the subsurface extension of our older sedimentary rocks at the correct dip. So what I've done here is, from our contacts at the surface, I've used a protractor to measure 35 degrees around and 35 degrees from the horizontal, and continued that bedding plane downwards. Okay? Now what I've done is continued these bedding planes on the left hand side of the fault as we look at it. I've continued them down at depth, but then I have stopped them at the fault. I haven't continued them straight through, and that's because if we look at the fault, we can see that the fault has displaced the stratigraphic contacts. We can see the displacement on map view. If we follow this fault along, at this point we've got a stratigraphic contact on the east side of the fault plane, but we can't see the continuation of that stratigraphic contact on the west side of the fault plane, and that's because there's been slip and the fault has displaced the contacts either side of them. So we've gotten to this stage where I've continued my stratigraphic contacts from the surface down at depth, and I've stopped them at the fault. I've also stopped this contact down at the dike, but because dikes aren't like faults, you don't generally have displacement when you intrude a dike, what I'm able to do is continue with a fair degree of certainty that contact through the other side of the dike. When this dike was intruded, the ground essentially opens up and magma is injected, but there isn't any appreciable slip either side of the fault plane. Okay, so that's why I can continue it on through the dike with no, taking into account no displacement. Now the left hand side of the fault as we look at it is easy to colour in, because we know that these rocks are parallel bedded. That's what they look like on the map, and we know we've got the top and bottom of most of them, so we can continue them at a constant thickness down to the fault. And because my cross section ends at A, I don't really know how much further this millstone grit rock extends towards A. So what I've done is taken it a little way, I've estimated it from the stratigraphic column, and then I've tried to dot in my level of uncertainty. What I'm trying to say is that beneath this millstone grit there might be other rocks. I don't really know exactly what they are based on the information from my cross section, and I don't really know exactly how deep I'd have to go to find them, but I'm just telling you that they might be there. Okay, the right hand side of the fault as we look at it is a bit harder because the fault has displaced the contacts by some unknown distance. I mean, unknown, we haven't got a definitive answer about what that distance is. However, we can't leave our cross section like this, right? It's unfinished and it appalls my sensibilities. So we're going to have to estimate where our rock contacts would be in the subsurface and reflect this level of uncertainty. So if you guys pause for a minute and just think about how you might do this, there are one or two methods that I can think of. So have a think for a few seconds and pause the video if you need. Okay, well, there's one of two ways to do it. The first way, and probably the best way, is to look at the stratigraphic column that's been supplied with the map. You can use that stratigraphic column and the scale that's come with it to estimate how thick each one of the units that you're currently missing from your section should be. So for example, here we've got a thickness for the Penrith sandstone, which we could measure on our stratigraphic column, convert it using our scale factor and work out its true thickness. We can also do the same thing for the millstone grit and for the underlying coal measures. for the coal measures and the underlying millstone grit, and then we can plot these thicknesses on our scaled cross section. If we were to do that, and it might take a little bit of mathematical working, we could then plot on our remaining contacts, showing them as dashed lines to show that we're aware that there's some level of interpretation about this. The other way that we could do this is if we took it back a notch. We could look at the repetition of the stratigraphy either side of the fault. And you guys are probably happy that this part of the Penrith sandstone and this part of the Penrith sandstone and this part of the coal measures and this part of the coal measures, this contact that we're seeing here is the same as this contact. Yep. So what's happened during this faulting is that this side of the fault has been pushed upwards and this side has been pushed downwards. That's why we've got this offset. Now if we're confident of that as an interpretation, then maybe what we could do is just mimic or copy this stratigraphy from the base of the Penrith sandstone on the left hand side of the fault and put it in on the right hand side. That would be fine if we're certain that what we're seeing here, this plane, is the same or would have been originally the continuation of this plane prior to the faulting. Okay, I'll try and show you both ways in my video of the lab. But whatever way we do it, we're going to interpret the continuation of the stratigraphy on the right hand side of the fault. Okay, at this point then we can nail our colour to the mast, and we can finish our cross section. And then again, what we can do is try and show that we understand that prior to the modern weathering processes, this geology would have continued above the surface prior to modern day erosional processes. Then what we can do is make note of our scale. In this instance, we didn't employ any vertical exaggeration. We didn't stretch anything. I've just kind of told a little white lie and said that the beds are dipping at 35 degrees, but I haven't stretched anything. I've just, flat out lied just to prove a point. So we can either just use a single scale or say explicitly that there's no vertical exaggeration. Then what I should do is include a column or a key and then label my rocks accordingly. So at this point we've kind of finished our cross section. We've got our rocks at surface, we've tried to show where the contacts are, where we're sure, where we're more interpretive, and we've tried to give a key and a scale so that people can understand it and relate it back to the map. Now if we were to compare this cross section that we've just made on PowerPoint together to the one that's supplied with the map, you can see that we're pretty good in terms of similarity. We've got this vertical dyke, we've got this almost vertical, what's the dip of that, about 80 something degrees, fault, which has displaced the Penrith sandstone on the left hand side relative to the right hand side. And then we've got these dipping sequence of Penrith sandstone, coal measures, and then millstone grit, which is what we've got. Penrith sandstone, coal measures, millstone grit. Alright, I hold my hands up and say that the dip of our cross section is different to the one supplied with the map, but that, if you remember, is because we just decided we were going to plot these rocks at 35 degrees so we could actually see the dips. Okay, so that's the process for making a cross section containing dipping rocks. The lab that we've got now relates to the Penrith sheet. It's the one that we've just looked at. So take some time to digest the map, have a look at it, and then have a go at drawing your own cross section through it. Thanks for listening. I'll see you next week when we'll talk about folded rocks. Okay, take care of yourselves, keep washing your hands, and see you when things are normal.